Alright, we're going to take a look at a couple examples using Wiens' law and the Stefan-Boltzmann law. Let's start with Wiens' law. So this equation tells us that the peak wavelength, which the book calls lambda max, is equal to some constant, which is 2.9 times 10 to the negative 3 meters. Now remember scientific notation here, that means we would move the decimal 3 places to the left. So this is the same as saying 0.0, let me check. I go 1, 2, 3, so there's 2 zeros. 0.29 meters, right? That's the same thing. Okay, but we're taking that and we're dividing by the temperature in Kelvin. So I'll put a capital K here so I know I have to use units of Kelvin. So we could write this either way, however more comfortable. There's sometimes we'll have to use scientific notation, but for now we can write it like that. So if I know the temperature of the star, I can find its peak wavelength, and if I know the peak wavelength, I can find the temperature. So let's just do each of those cases. Let's start with the star, the North Star, Polaris. So Polaris, I just looked this up, has a temperature of 7,200 Kelvin. Okay, now if I were to write that in scientific notation, it would be 7.2 times 10 to the 3 Kelvin. Sometimes it's helpful to write both numbers in scientific notation. Now I'm going to do all these calculations using scientific notation because it's good practice and I think it's more useful. Once you get the tricks, you can do it pretty quick in your head. So let's take a look here. So that's the temperature. I want to find what the peak wavelength is. So that's what I'm trying to find, is lambda max. So I can use this equation just as it's written. And so I'm going to use it in scientific notation here. I'll say 2.9 times 10 to the negative 3 meters divided by the temperature in Kelvin here. So 7.2 times 10 to the positive 3 Kelvin. Alright, and that's going to give me this wavelength. So let's check this out. Now I'll use a calculator and I'll type in 2.9 divided by 7.2. And that equals 0.40. Okay, and now I would multiply that by, I'm using scientific notation here, so now of course you could just type this whole thing into your calculator, including the scientific notation. I tend to just look at the first few numbers, right? So I did 2.9 divided by 7.2, and then when I look at scientific notation, it's relatively easy to do this because if I'm dividing by a number, that means I subtract the number from the exponent. So I have negative 3 and I divide by 3, it means I'm subtracting an additional 3, so I'd end up here with negative 6 meters. Now this would be an acceptable answer, but in proper scientific notation we'd have a non-zero digit up here, right? So really we should write 4.0 times 10. Now since I went to the right, it means I took one of these away here. Let's see, I think it means I'm at negative 7, right? Because I'm going that way. That makes sense. Okay, now sometimes this again is an acceptable answer, but sometimes if we want to relate this to the color of light, it's helpful to write this in nanometers, right? Because we sort of know that the visible range goes from roughly 400 nanometers of blue light over to about 700 nanometers of red light. So sometimes it's helpful to put it into nanometers. Sometimes I might ask for it specifically in nanometers. What's important to know is that 1 nanometer is equal to 1 times 10 to the negative 9 meters. That's the relationship between these. So if I were to rewrite this number, 4 times 10 to the negative 7 meters, I could write this in nanometers. And since it's negative 9, that would mean I move two more places this way. And so it would be 400 nanometers. It takes some getting used to, right? I have a lot of experience with these units, so I kind of know which way to move the decimal place. But it can be a little tricky sometimes. So there's an example, okay? Polaris is a hotter star, and hotter than our sun, and you can see that its peak wavelength is bluer than our sun, so that kind of checks out and makes sense. Okay, so let's do a different example, a different type of problem that we might do with Wiens' law. Let's say that I know the peak wavelength, but I'm trying to find the temperature. Let's suppose that we know that the peak wavelength coming from some object is equal to 9.7 times 10 to the minus 6 meters. 9.7 times 10 to the minus 6. So now we could put this into nanometers to say what color is this or where does this fall. So if I'm going to nanometers, I need to go to 10 to the minus 9, right? 10 to the minus 9. So it means I would move the decimal place 3 places here if I'm thinking about this in nanometers. So this would translate to 9700 nanometers. Now we know that visible light, right, goes from 400 to about 700, and so this is a longer wavelength than red light, and so this would be pretty squarely in the infrared range of light. So okay, so this is infrared light. The question is how hot must this object be if this is its peak wavelength? So we're going to have to rearrange this equation, right? So I have lambda, and I know that that equals the 2.9 times 10 to the negative 3 over temperature. And so to rearrange this, right, we're thinking back to algebra. I'm going to multiply both sides by temperature, multiply by temperature over here, and then it cancels out the temperature on this side. But to get temperature by itself, I'm going to divide both sides by wavelength. Right, divide by wavelength, it cancels it here, divide by wavelength. So ultimately, I could rearrange this and I end up with that the temperature, if I want to solve for that instead, is just going to be 2.9 times 10 to the minus 3 meters divided by whatever that peak wavelength is, lambda max. Okay, so we can figure this out. Let's find this temperature. So T will equal 2.9 times 10 to the negative 3 divided by 9.7 times 10 to the minus 6. Now, if you want to just type this in your calculator, I just want to remind you that to write scientific notation, the way you could type this in your calculator is you would type 2.9, and then you'd look for this double E button. Double E means times 10 to the power of. So you type that, and then you type negative 3, right? And then you could divide that by the same thing, 9.7 EE 10 to the minus 6. So if we type that in, we get 200, and it looks like 99 Kelvin. So that would be our temperature, and this is roughly room temperature. I mean, this is maybe 75 degrees. What's interesting about this is the temperature of our skin, right? Our skin's generally at room temperature, and so that means that our skin at this temperature is glowing, is shining, is giving off light of this particular wavelength, this infrared light. And of course, this is familiar with this, like thermal vision, right? Like night vision cameras are picking up this infrared light that people's bodies are giving off. So we're all literally glowing at this wavelength of light. Now let's turn our attention over to the Stefan-Boltzmann law. So Stefan-Boltzmann equation looks like this. E equals, and we have some constant, this sigma, right, times temperature to the 4th power. So this is interesting. We have this 4th power in here. We rarely see that anywhere in physics or astronomy, that there's a 4th power. But nonetheless, we can see that. And so this total energy that's being given off by this object depends on temperature to the 4th. And we saw that with the simulation, right? A small change in temperature yielded a very large change in the amount of energy that's given off, or the brightness of this star. Now, because of this sigma, and it gets a little complicated, most of the time when we're using the Stefan-Boltzmann law, we're going to do our ratio problems, right? Where we're not looking at specific values of temperature or of energy, but instead we're looking at how they change. And by doing so, right, this equation will simplify. So let's take a look at an example where we say the temperature becomes 4 times greater. So maybe I'm now I could give it to you a couple different ways, right? I could say the temperature is 4 times greater, or maybe I say there's 2 stars, right? I could say the temperature of star A is equal to, let's just say 1,000 degrees Kelvin, and the temperature of star B is 4,000 degrees Kelvin. And then I could ask you to compare the energy that these 2 stars give off, or I could just tell you that one is 4 times bigger, right? Either way, you're looking at the ratio of these 2 things. So you'd say like, well, the star B to star A is a ratio of 4, so we're gonna use that. Now, the ratio problem, as we've seen a couple times before, when we're asking how it's changing, anything that's constant just goes to 1. So we know that temperature is changing, and we know the energy is going to change in response, but this sigma is a constant. And so what that allows us to do is just basically ignore the sigma, right? It becomes 1, right? Because we're saying the ratio of sigma to sigma is just 1. And so for temperature, I'm going to put in a 4. Again, the really important thing with ratio problems is that we remember to keep the exponent. So I have here is 4 to the power of 4, right? And that equals 256. So when I say here that energy equals 256, what I'm really saying is that the total flux given out by this star is 256 times bigger in star B than it would be in star A. Right, so that's the type of problem that we can solve with this equation. Now, likewise, we could do the opposite, right? I could tell you, for example, that maybe one star has 16 times the energy. So star B, we'll just say, right, has 16 times the energy. And I could ask you to compare their temperatures. So this is a case where for E I would plug in 16, and since it's a ratio problem, again the sigma goes away, and I'm left with just t to the power of 4. And so you'd have to solve for this t. Maybe you haven't solved something that's raised to the 4th power before, but there's no button for that on your calculator. There's no like 4th root button. That's what we need to do is take like the 4th root. So I just want to show you how you could solve it this way. To solve for t and to undo this 4th power, what we'd have to do is take both sides and raise them to the power of 1/4. Right? We raise it all to the power of 1/4. So you can type that on your calculator. You just like write the little caret to the power of 1/4. And you'd probably have to use parentheses. So if you type this in your calculator, you'd be typing in 16. You'd look for the little caret button, and you'd type in probably parentheses 1/4. Okay, and that's going to take that's going to take the 4th root of 16. And so I'm going to do that, 4th root, and I end up with 2. Oh, I should have figured that one out. 2 to the power of 4 is 16. Okay, so this tells me that if one star is 16 times more energy coming out of it, it's only twice as hot. Right? So that told me the temperature difference, that the temperature is going to be twice as hot. Okay, so those are the kind of problems we could solve with both Wiens' law and with the Stefan-Boltzmann law.